I'll start recording. Okay, welcome to the physics section of the meeting today. And today's discussion will be on introduction to data science. And after the introduction to data science, though, then Samrat will continue to give a description about AI implementation and a recap from last time's lecture. Okay. So today we will cover what is data science, important Python libraries, the common data structures, what is data analysis, data visualization, and at the end I've put resources used for this meeting. Okay, so what is data? Does anyone want to answer that?
Data is just information that we collect and interpret to do various other tasks.
Yeah, that's correct. So data is information which can be collected and then utilized. So there are numerous definitions. And this is one of the most basic one. Okay, so now what is data science? In the most basic terms, it can be defined as obtaining information or and insight from the given data. And how is data collected? So data can be collected in various ways, and most common would be to go on the internet and download the data in our case. Also, data is collected by companies. For example, when you go on Google, you search for something, and then Google will collect that data, analyze it, and then give you predictions based off it. Data is also collected within the companies to improve products, boost sales. And in this semester, we will deal with pre-processed data available on the internet, but we can also in the future collect web data using web scraping. So web scraping extracts website data and converts it to usable format. So you could go on Amazon and use a web scraper, and so you will get all the product information. For example, if you're looking for an iPhone, so it will give you the cost, it will give you the reviews, for example. But then you would ask, why is data important, right? So Southwest Airlines nearly saved $100 million every year just by analyzing the data they already had. And by analyzing the data and the flight times, they reduced the time a plane would spend on the tarmac. And so the plane would be in the air for the maximum time. And that saved them $100 million a year. Even the IRS saved about $2 billion by analyzing data and predicting identity fraud and improper payments. Does anyone have any questions till now?
We got it.
Okay. So next we'll discuss the important tools used for data science, and Python is the most versatile tool. Python, R, and SQL comprise of the most important languages for data science. Even Tableau is very important for data visualizations. We will use Python because of its versatile nature and the Python libraries we have. So these are just a few examples of the numerous Python libraries you will find, and these are the most important ones for data science. So let's talk about pandas. It, it is one of the most important libraries for data manipulation and analysis, and we will use Panda for cleaning and processing the data. The import declaration is given here, and that's how you import a library into your Python script and then use it. Next, we'll talk about NumPy. It is very important for all numerical operations, and also we will use it as like we have to do a lot of operations based on the data we've already been given. And NumPy is also used for creating many other libraries. So it is a very important library. Other libraries like Beautiful Soup are used for web scraping, and matplotlib are used for data visualizations. Then we'll move on to data structures we will use in Python. List, as the name suggests, is a very basic collection of elements and is mutable. So anyone who doesn't know what mutable means, it means that you can edit the constituting elements of the list. And this is the way you declare a list using square brackets. And then we can move on to sets, which are an unordered collection and are also mutable. And they can be declared using curly braces. A tuple is maybe more advanced than a list, but it's very important as well. So it's a collection of objects which is ordered and immutable. So you cannot edit the objects within it once you declare it. It is declared using round brackets. Tuples can be sliced, which means you can take a piece of the tuple. So how you take a slice of the entire cake. And concatenated, which means you can add two tuples. So if the first tuple is 1, 2, 3, 4, and the second being 5, 6, 7, 8. So if you do the first plus the second, it will give you 1, 2, 3, 4, 5, 6, 7, 8. And they can also be compared and so on. It is a more complex data structure than lists, but it it can do many important functions which we'll require. Next is data frames, which is the most important. Think of data frames like spreadsheets or Excel sheets. So data frames are two-dimensional labeled data structures with columns, which can hold potentially different types of data. So like one column could be like a list of functions, the other could be a tuple of numbers. And they are the most important data structure for storing and raw and processed data. And thanks to the pandas library, we can use them. We can import pandas and then probably read like CSV files. CSV files are like Excel files used for storing raw data. And once we do the read the underscore CSV function, the data is automatically converted into a data frame in Python, which we can use. And the second data frame function is a general function, and you can basically you can create your own data frame using that, or you can merge two data frames using this. This is an example of a .csv file, and it's from the MNIST fashion dataset, which we will be covering next week. And this can be imported into Python using the data frame, thanks to pandas. Does anyone have any questions? Okay, so next we will talk about data analysis. Data analysis is the process of collecting and organizing data in order to draw helpful conclusions from it. Why is it important? It is important because by analyzing the data, we can draw conclusions. And with those conclusions, we can improve, understand, and predict future outcomes of the data we are given. And how can we go about doing it? So first, we begin by identifying the relevant data. Next, we would obtain it using the internet or using web scraping and obtaining our own data, or also creating our own data. The next would be processing and cleaning the data. And after that, we would be analyzing the data. It can be done using data visualizations, so, and also by training a machine learning model to predict and tell us what the best outcome could be. So, for example, we can use, if we want to train a model, a machine learning model to read numbers. So first we would begin by identifying what is the relevant data. So we would need images of the of the numbers. And the next would be obtaining it. We could probably write it on our own and click photos or go on the internet and we'll find a nice data set for it. And after we obtain the data set, we would have to process the data, put them into one place so that we can feed it into a machine learning model. Next, we'll talk about data visualization. Data visualization is the graphical representation of information and data. In Python, we will mainly use matplotlib for basic data visualizations. The import declaration is given here. We can create basic scatter plots, line plots, histograms, and even more complex data visualizations. This is This is an example of a histogram on the left and a box plot on the right using matplotlib. And then we can also do complex tasks. Like if we have a 2D array, we can actually convert that and visualize that into colored representations. So each of these colors would mean a number. And we could also plot 3D images using matplotlib. And then there are advanced data visualizations. So this is a animated visualizations of life expectancy in different continents over the years. And this is done using the computer language R. And this is a live visualization of the tools using Tableau, which is another tool we can use for data visualization. As you can see, it has many advanced functions. We don't really need to know any of them, but it is important to know how and why we would finally use data visualizations. So I've compiled all these resources used today. All of them are hyperlinks. You can go on the slides later. And thank you. Does anyone have any question?
It was like I have a question about like matplotlib. Matplotlib is actually just like just like graphs, essentially, just portrays the graphs using like the data that you're given, pretty much.
Yeah, pretty much.
Could you have 3D plots?
Yes. The one on the right is a 3D plot.
That's cool. That's cool.
So I think now Rohit and Samrat will continue with the AI implementation part of the meeting today.
Sounds good. Good stuff. Good stuff, Shanil. Remember, guys, this data science stuff, at least in what we have planned out, and we're going to announce it by the end of the meeting, what we have planned out and in store for all you brave, I don't know, soldiers. I don't know. You guys are basically going to work on stuff that doesn't fully involve like all the complicated data stuff yet, but it's important to know it in general because you can't have one without the other, right? You can't have like AI or machine learning without data for it to learn from. And what Chanel just talked about is the stuff that goes on before an AI like trains on it and tries to make a prediction out of it. Businesses often use that prediction to try to convert that data into some sort of insight as to what they can do to like, you know, run their business better, whether it's like maximizing profit, cutting costs, improving customer satisfaction. All those things usually are derived from insights that can be drawn from that data. So the tools that Channel was mentioning just now are used to sort of either manipulate or visualize that. And that brings us to the next point. What do you do once you manipulate / visualize them? You have to implement some sort of model to basically try to draw some predictions, right? And that's where AI and machine learning comes in. So today we're going to talk a little bit, Samrat and I are going to talk a little bit about implementing AI concepts that, you know, you guys were so rushedly introduced to in the previous week. But if you have any questions, as always, feel free to stop me, put them in the chat, and or just like, you know, oops, catch us outside meetings, and we're happy to help. So without further ado, implementing AI concepts in Keras. First thing, we're going to revisit some AI concepts. 3 types of machine learning: supervised learning, which is you take data which has features and labels, you learn from it, and then in the future, if given some features, you have to find the right label. So you're predicting based on learning from previous examples. You have unsupervised data, which, you know, we're not really focusing on right now, but it's out there. It's where you take data without labels and you try to cluster it, find patterns, and try to like see what's common in certain elements of it, and you can bucket it. The third thing is reinforcement learning, which is taking real-time data. You don't have like a data set, and then you learn from it like on the fly, and then you try to decide on the best action to take. Example, video game playing bots, or someone mentioned last time, stock market. This is still a new field, and there's many different kinds, like subtypes of reinforcement learning, but we don't need to go into that as of now. Supervised learning, I have a question for you guys. I am thinking of some number, all right, and I can give you its features. It has a lot of round edges. There's no jutting appendages on this number, and it's a massive circle. Someone tell me what number it is.
0.
Perfect. Okay, that's it. Yeah, it's a 0, right? So what do? We identified a few features based on knowledge that we had about what numbers look like, right? And then we try to map those features to that number, and we're able to deduct that it's a 0. And that's what an AI essentially does after training on tons and tons of numbers. It tries to identify these things and then bucket them 0, 1, 2, 3, whatever. This is actually a picture of the renowned world famous MNIST data set. More on that soon, but not today, but soon. And yeah, moving on. Inside OneNote, hopefully you remember this, but if not, no problem. Suppose we are a recommendation. No, wait, I used that last time. Okay, suppose we're a weather predicting algorithm, right? I feel like I use that too, but I don't know. I'll just go with it. Suppose we're a weather predicting algorithm, and we have a few features, right? We have things like yesterday's temperature. We have something like today's humidity. We have something like, I don't know, average wind speeds, I guess. And we're supposed to predict whether it's going to be sunny or not. It's a simple problem, right? Whether it's going to be sunny or cloudy today, one of two options. So we take each of those features, those inputs in, we decide how much we want to like give importance to each one of them, right? Maybe yesterday's weather is less important than today's wind speed. So maybe we might weight yesterday's humidity like less than today's wind speed while determining our answer, right? And that goes in as a weighted sum, x1 x1 times w1 plus x2 times w2 plus x3 times w3. All of that goes into the sum. We add some bias to it, which is just another parameter for the network to figure out if it wants and what value it should be. It's something internal. We don't need to really know what the value is. We can if we want, because technology. But yeah, then we get an output, which is, a partial output. We call that Z for output. I don't know. We can apply some function on it. These are called activation functions. I'm going to go over them real quick in a bit. And we get the actual output, which is the prediction as to whether it is sunny or cloudy, right? So that's how a weather predicting perceptron. A perceptron is when the whole AI is just this one node. That's when it's called a perceptron. If you have multiple nodes in the AI, you call it a multi-layer perceptron or a neural network, whatever rolls off the tongue worse. You have these two mathematical equations summarizing what's happening to each of these values. It's not that hard. It's like the linear equation that we saw last time. And then the labels here, you have weight, bias, and then activation function. Are we good so far? Stop me if you have a question right now. Because this is like I know like last time was sort of rushed and there was a ton. That's why I just wanted to like bring these in real quick before Samrat gets to implementing these things in Keras. So that is the whole thing about like one node, what goes on inside one node. Activation functions, we just saw them. They take in some sort of input and they try to like produce some output that is useful or meaningful to us. We saw a few examples last time. This one was called, someone tell me what this one was called, if they can remember. If not, that's totally cool.
ReLU.
Sigmoid. Okay, ReLU is coming up soon, but this is a sigmoid. And that is the equation. You're welcome to plug that into like Desmos or your graphing calculator and play with it. It's a pretty cool equation.
Remember, it's shaped like an S.
Yes, a sigmoid. Yes, cool. Thanks. It is shaped sort of like an S. So S for sigmoid. This one, someone already said it, but okay. Yeah, it's a ReLU. And then the last one, someone tell me. Another S-shaped function, but not the same as sigmoid. Can someone guess?
Is that hyperbolic tangent?
Perfect. That's it. All right. We just say 10H, but that is what it is. Hyperbolic tangent. All right. And then this is sort of like an outlier within the activation functions. This is called softmax. If you have some sort of random raw values and you need to figure out a probability of that one being the right answer, right? Like suppose this is what the AI was thinking for sunny. This is what it was thinking for cloudy. We need some sort of probability of being the right answer, right? So we need some function to do that. And essentially maybe it guesses that there's a 88% chance that it's going to be sunny. So that's that. That's the softmax activation function, usually applied only on the last layer of the neural network. How neural networks learn? They take in labeled data. I'm just talking about supervised learning for now. They take in labeled data. They do some multiplication and addition. They deem what the values are, whatever is necessary. It's up to them. We don't manually tweak each internal value. They apply an activation function. We just saw those. They produce an output, and then they have to optimize. Like initially, we can't expect them to nail it, right? So they have to spend some time, learn over more data, and adjust these factors, these weights and biases, which are what numbers they multiply or add to the data. That's it. That's 5 steps. Optimization, what goes on there? You have a prediction, right? Suppose it's like suppose you're predicting it's cloudy, but it ends up being sunny. So you're checking, oh my God, I said it was going to be cloudy, but it's sunny, right? So you're checking, and then you compute the difference between the two. There's like an actual whole science within this, but we don't need to go too deep into it. Because on a conceptual level, it's more than enough for what we're doing this semester. It tries various weights and biases over like, more and more data. It minimizes the cost, which is this difference here. There are multiple algorithms, and you can choose which one works best. There are several, but like Atom is the most general purpose, best used one. And then again, weights and biases are parameters. So we cannot change those for the network, the neural network. But we can change what are called hyperparameters, which are things like the size of the network and the activation function and, like the actual optimizer and anything else that the human can tweak to make it learn better. As a summary, that is cost on the y-axis. And that is how the AI plots over time what the cost is when it tries different weights and biases. And then it figures out the best weights and biases to reduce the cost. Are we good so far? Silence is acceptance. All right, reading an image. So last time I introduced this simplistic example. I realized that was a lot to pop up onto the screen, but it's a review. We have a simple image, 30 pixels by 30 pixels by one color channel of some strawberries. And we need to try to figure out whether it's a strawberry or an apple. All right. And I mentioned that these weights connect these layers. It's not really the full picture because things aren't that simple in real life. Like, you don't, there's a ton of processing you need to do to data to get it down to 30 times 30 times 1. Some data sets are that simple, but the useful stuff isn't usually like that. Like, taking in something from a video, or, just like reading a document. You can't expect to like gain information from 30 by 30 by 1, right? That's terrible. So how an AI actually sees it. Okay, I'm taking a slightly more complicated example. Things can get way bigger than this. You have 120 pixels by 120 pixels. After it has been processed using all of the libraries that Shanil talked about, once you process that, you get this image. And I wrote a 3 here because that's 3 color channels. Anyone want to tell me what the names of 3 color channels are in computers?
RGB.
Perfect. So red, green, and blue. Those are the 3 color channels. Each of them will have some sort of value between 0 and 255. Yeah. So what happens in an actual AI that can see an image? There's more stuff, right? You have something called a convolutional layer, which just means it has like a bunch of tiny little flashlights, and it just goes left to right all the way down through the image, trying to process it bit by bit. It's like if like you were in a dark room and you turned on a flashlight, right? You can only see the room bit by bit, but once you look all around, you have a good idea of what's in the room. So that's basically what this does. Pooling, it's sort of like brings together all the tiny parts that it saw in the convolutional layers. In the filters of the convolutional layer. It tries to like bring them all together and try to see the thing as a whole. And then you have your actual neural network that does the thinking. It sees the image until here, and then it does some sort of prediction off of what it's seen till here. So in the project, we are going to do some of like all this stuff is like pretty complicated, so you don't need to worry about it. But worry about this for now, because this stuff is the key stuff. So the first layer is flattening. It takes this, which is not in a single dimensional array. We're going to get to like, scalars, vectors, and matrices in a bit. But it just takes something that's multidimensional and turns it into a gigantic vector. If you don't understand what I'm talking about, that is also fine because you'll still be able to do the project. It's just good to know the stuff. Dense layer, which just takes the input to the next level, adds some more weights and biases in, tries to do some thinking, and then produces an output. And that's how you actually process. Oh yeah, and then you need to optimize after every image to try to like refine your understanding essentially. And that's the circle of life. So this is a common algorithm in computer vision. It's called a convolutional neural network. A fitting name for something pretty annoyingly complicated here, but Keras makes it really simple. Don't worry. But these just try to like go over the picture in convolutions. I guess that sort of makes sense. Any questions?
Would you just tell us what flattened and dense mean as such?
Okay. So when the data comes to the pooling layer, I'm assuming you're cool, right? Till the pooling layer, is everything okay?
Right.
Right. So it's seen the room and it tried to detect everything together. It just pieced together all the little puzzle pieces. And then this thing is not in the right mathematical dimensions, right? Everything in AI flows in something called a tensor. And a tensor is nothing but like a conglomeration of tiny individual scalar numbers, right? We're going to visualize that in a little bit, but essentially it is not in the n by n dimension that it needs. So this flattened layer converts that into that appropriate dimension for the rest of the network to do the thinking. Did that help?
Yeah.
Okay.
You can also think of it like taking a square, right, and like turning it into like a line.
Yeah,
Yeah.
sort of like that. Except like the square is like in any number of dimensions.
Yeah.
Okay.
Right. So you're simplifying the data so the network can process it.
So essentially like the convolution. So is it okay if I just repeat what you said just to clarify?
Yeah, go ahead.
So like convolution just basically means kind of just separates into separate like sort of images, I guess. So I'm assuming.
Right.
The
Little tiny parts of the image. Yep.
little tiny parts, okay. And then the pooling kind of just separates it, I think. Kind of just
Not separates, but it puts it all together. It tries to take the most important parts of each of the little parts that the convolutional layer split it up into.
Okay, so it just takes little parts and just kind of sort
Tries
of
to see the whole picture.
see the whole picture, yeah.
Right.
And then flatten just means like kind of like put it all together, just kind of
Yep.
one thing. And then to dense it out, it just makes it like kind of wider, I think, thicker.
Not quite. This is only called a dense layer just because nobody knows what's going on inside it. It's the part of the network that is completely autonomous, and we just don't really we don't know how to explain what goes on in there, except we just know there's numbers and it's multiplying something and it's somehow getting the output. More on explainability later. But dense is just another way of saying a fully connected layer in the middle of the network. It's not necessarily widening anything. It's not really like a specific function. It's just more neurons, more brain cells to think. Is that
Yeah, that's good.
yeah? Okay. Any other questions? Remember, you do not need to worry about the specifics unless you're really interested. We are more than happy to talk outside of meeting time. But for now, you just need to know on this abstracted level what exactly seeing looks like. If you get my meaning. All right. So remember, like when I started out in my internship, I was exposed to only like a certain limited range of AIs. I still got to see other types in action, but I kind of thought for the longest time that what I was working on was how all AI felt. But no, AI is not like that because you can modify the algorithm in any number of ways to solve almost any number of problems. So there might be all types of problems, right? You might have customer records as a bank, and you need to figure out whether that customer is going to leave or stay, right? So you're trying to assess attrition. And this might have information about the customer stored in a database, like what Shanil was saying. You can pull it up in a data frame, which is nothing but a fancy way of saying an Excel sheet. And you can try to identify factors that are leading to them leaving or staying. And you should know what to do as a company and what not to do. Other examples, again, recommendation engines, and I don't know why my examples always like go to those two, because those are just like pretty big ones. But I will think of more and I will tell you more outside of meeting times. Um, but you can solve a wider range of problems than just seeing things. Oh yeah, customer reviews, right? So you're on Amazon and then you go down and then you see like this product has been given this many stars, and then some grumpy guy would have written some sort of essay about it next to it. And the AI is supposed to go through that essay and try to identify his sentiment, right? That sentiment analysis. So it's trying to figure out whether he was satisfied, whether he was like upset, whether he was disappointed, also upset, and so on. So that is essentially like it's a wider range than what we are showing you. But this semester we're focusing on computer vision, so we're just sort of leaning everything towards that. Any questions about AI? We're done with the AI review. I hope it wasn't too rushed, but please tell me if you have any questions. And a 5, and a 4, and a 3, 2, 1. Sammy, all yours, my boy.
All right, cool. Can you hear me? All right, cool.
Yes, sir.
I have to remember to make this video thingy smaller so it doesn't cover the entire presentation like last time. I'm just gonna put here. Cool. All right, and the moment everyone's been waiting for, how do we actually code all this stuff that we've learned? How do we actually like, do it, right? So essentially, broadly, we're going to be using this Keras is a library, right? Not mistaken.
Yeah, it's a library. Like it's just another API essentially,
Right.
And it's written it's written to be compatible with TensorFlow.
Yeah. So basically, we're basically going to be using Keras, which basically goes along right with TensorFlow. It's like peanut butter and jelly, right? Like think of Keras as jelly and the TensorFlow as peanut butter. You just work together really nicely. So we're going to be using that to code all this stuff we've learned. And I guess the first thing to talk about, since we've been talking about TensorFlow so many damn times by now, what exactly is a tensor, right? So essentially, what the TensorFlow library does, rather how machine learning programs work in general, it's essentially a flow of tensors. And as Rohit mentioned earlier, tensor it's essentially a way to transfer data, very broadly speaking, right? So there's many of different types of ways you can like transfer data. Okay, I'll give you an example. So I wanted someone to answer the question. When you buy eggs, right, to like eat or something, what do they come in? Anyone? Any egg eaters here?
A carton.
Yeah, exactly, carton. And we know that cartons can come in like dozens, like that mean 12 eggs in a carton, or 6, half a dozen, which means 6 eggs in a carton. And how are those cartons delivered from the farms to the grocery stores?
They put them in boxes.
Yep, exactly. They put them in boxes. So what we have is like, we put the eggs in cartons. When you stack a bunch of cartons together, we put them in a box. And we stack a bunch of boxes together, we put them in a truck. So we're essentially just like, those boxes, those cartons, those trucks, those are basically just methods of transferring the eggs, or in case of programs, data or numbers, right? So what tensor really is just a way of transferring information to the machine in different stages. And we have different ways of we can differentiate tensors from like different forms of transferring data, right? So a scalar just means one value, right? A vector just means multiple values, but in one dimension. A matrix is like a m by n dimensions. So like you can have a 2 by 2 matrix, which is what we have right here. So it has 4 entries total, or 3 by 3, which would be 9 entries, so on and so forth. Then finally we have tensor. Tensor, I really want to hit home here. It's just a very general way of stating this. It could be a vector if we're trying to flatten it. So it could look like a vector if we're trying to flatten it for a computer vision problem. It could even look like a matrix, or yeah, it could be any dimension really. And I think Rohit wanted to bring one point about this.
You read my mind. I was just gonna ask if I could step in for a second. Essentially, just like Samrat was saying, these are different like ranks almost, and they're called ranks. A scalar is like the equivalent of a point, so we call that a 0 rank tensor. A vector is a single rank tensor, a 1 rank tensor. Matrix is 2 ranked, and then a tensor is like n ranked. You can have how many ever dimensions you want, and ultimately, like we mentioned earlier in the flattened thing, it'll get straightened out at some point because the network needs to process it. But there's some sort of complexification when you put the eggs in the truck, and simplification when they need to pull it out of the truck that's happening in an AI. That's all I had to say for now.
Cool. Yeah, I noticed some people in the chat said my voice is screwed up. I don't know, honestly. I wish I had a better microphone on my laptop, but
He was born with it.
yeah, I'll figure it out. But moving on, if this could go to the next slide, that would be great. Okay, there we go. Did I skip something? Okay, no. So basically, there's 3 parts to any machine learning model, right? There's a sequential model, there's the, oops, I gave it away. Sequential model, there's optimizer, and there's the fitting. So first, we have the sequential model. What's the sequential model exactly? It's basically what we went over in the AI recap. So all these layers are what we call the sequential model. Sequential meaning like we have the first layer, second layer, etc. Right? So there's layers upon layers in the sequence. That's all a sequential model is, right? So the way we actually do this is that we define an object called model. Remember back to the Python tutorial, how we declare stuff. An object is the same way you would declare any other variable, like integer or string or anything. So declare object called model equals, and we use this notation for pretty much a lot of the things that we're doing. TF, which stands for TensorFlow, dot Keras, dot sequential, and that's the beginning of the function. And in the sequential function, we pass in an array. What does that array contain, you ask me? Well, it is essentially all the layers of your neural network, right? So if we go line by line, I have some fancy animations to show you. So the first one is a flatten layer, because we say tf.keras.layers.flatten, and within that flatten function, we put the input shape. Input shape basically means, it basically corresponds to what you're putting into the flatten layer. So in this case, we have a 30 by 30 by 1 image. So accordingly, we put the dimensions 30, 30, 1, right? So you just need to tell this layer what it needs to flatten, what it needs to, like if it takes in something that's like zoop, it shrinks it to zoop, 1 dimension. That's exactly what flatten means, right? And then the second layer, which is circled by this cute green box, is going to be our first dense layer. So we say tf.keras.layers.dense, and within dense, we put in 3, which is the number of neurons or nodes or what have you. So we have 1, 2, 3 neurons in this dense layer. So we put the number 3 in the parameter. The next parameter is, well, yeah. So the last parameter, you have to specify the activation function. Remember back to when we defined what an activation function was, like ReLU, sigmoid, all that stuff. That like takes a big range of numbers and tries to squish them in a range between like 0 and 1s, for example. So in this case, we chose an activation function ReLU, right? And you can basically use this notation tf.nn.ReLU. Instead of nn.ReLU, you can put like nn.singleoid, etc. Right? So you can just pick your activation function. Then the last layer is, of course, it's another dense layer, but it will be the output layer, right? So it refers to these two outputs. This image is either a strawberry or it is not a strawberry. So accordingly, we passed in dense parentheses 2. 2 meaning the number of outputs, which is either not a strawberry or is a strawberry. Then the activation function, since this is an example like directly related to the strawberry image, we're going to be using softmax, right? Because we need a probability. We need to predict the probability of whether the image is a strawberry or not, right? And then we close the array. So this may look confusing at first, but that's just because like I wanted to space it out. But essentially, to recap, we're just passing in an array or a list of layers into the sequential function, right? And we're specifying what each layer, how many neurons, which function it needs in each line of code. Yeah, I think that's it for just, and keep in mind this has 3 layers, 1, 2, 3. Cool.
You can set the number of layers. You can just add how many ever dense layers you want. You probably don't want too many flattened layers because that's not going to help. And you probably don't want multiple output layers. That's probably not going to help either. But you can decide in the middle how many brain cells you want to add to the neural network.
Yeah, and keep in mind, you don't have to memorize this per se, because there's this great thing called documentation, which is basically the Bible for programmers, that will essentially give you the exact notation for each of these things. So no need to memorize it. You just need to know the general whoop-de-doo of it. I don't know. I can't speak English today. I'm sorry. The next thing, second thing is optimizer, and yeah. So the optimizer, like we mentioned back in the previous slide, it basically, this is how it sort of learns. It improves upon itself. It tries to minimize the loss from the previous iteration, right? So we basically just take the same model object and we use a dot, right? And dot basically means, hey, if you take any object, which in this case is called model, if you just put a dot next to it, whatever's right after dot, it just does something to the model, right? So very simply, if I had an object called Samrat, so if I said Samrat dot get name, it would return me a name, right? So in this case, we're applying an optimizer to the model object. So we specify an optimizer. In this case, we're using atom optimizer, and then we specify the I think Rohit wanted to say something about the loss parameter.
Yes. So again, there's a ton of different loss functions just because it's just a whole different branch of mathematics. It's pretty fun if that's your thing and you want to explore it. For this purpose, we just chose like one that can solve this problem just to show you for today's slide, but there's a ton out there. So the loss function is essentially what determines by how much it should play with the weights and biases between each image. While it's checking one prediction and the next, it needs to figure out, all right, I'm going to take a gigantic risk and I'm going to like do a gigantic leap, right? And as the loss function is plotted out, when the network takes several steps, you get this sort of curve. And remember, it is not two-dimensional. We're making it look pretty simple here because it's just a y-axis and an x-axis. But for students of multivariable calculus, you're going to get an n-dimensional graph, essentially. And you're going to have mountains, valleys, local optima, global optima. It gets really, mathematically fun, interesting, intricate. But Keras has abstracted all of that for us. You just need to pick which loss function and which optimizer you want. That's it.
And you wanted to say something about the metrics, right?
Oh, right. Yeah, the last thing. There's multiple ways that you can check how well an AI is learning. One of them is just called accuracy. You'd be surprised because like that sounds like the metric, but there's multiple other metrics out there. We're trying to figure out something fun for a session way later on performance metrics, but for now, accuracy is good enough.
Yeah. And as you can see here, there's no array. You're just passing in parameters, right? So like optimizer equals atom, blah, 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 loss equals this, metrics equals this. So yeah, that's the thing on compiling the model with optimizer. Okay, lastly, we have fitting. Now, fitting is essentially, think of it as like running your model in a way, right? So if you have a normal program, if you take 131, 132, and Eclipse, there's like a cute little green button that says play. Side note, you won't have that in 216. But anyways, yeah, it's essentially the same thing as running a program. So we're running the model that we've created. And the way we do that is that we use the dot operator again. So model dot, it's like, hey, model, do this. So the thing it's doing in this case is it's doing a fit function. Within the fit function, you have to pass in the data set, which we've named clean train data set. And keep in mind, this data set is cleaned and processed. So basically, in this case, it would be the pre-processed data from an image, whether an image of a fruit. We don't know if it's a strawberry or not, but it's some image of a fruit. Sorry, it's multiple images of fruits that are either strawberries or are not strawberries because it's a data set, so it has multiple entries. Epochs, recall back to the metaphor that we used. So basically an epoch, it's like basically reading a book from, actually why don't you take this one? I said it way better.
No problem. Epochs are, I mean, some people say epics, but that sounds like epic. And I don't know. I like saying epoch. It sounds more spoopy. But epochs are essentially how many times you read the book cover to cover, right? So you're reading some textbook or like some novel. How well you know it is usually some sort of, it depends on how many times you've read it end to end. So if the model has 5 epochs, that means it went through that whole data set. It might have 10,000 images, for example, in the data set. The model went through 10,000 images 5 times. That means it went through 50,000 images, repeated images. And then the last part is how many images you're sending in a batch, right? You don't need to send in an image one by one because that's going to take too long. So what we do is we chunk it into bunches. They're called batches, and they're like the equivalent of reading a chapter in a book, right? A book it consists of certain chapters, so many chapters. So epochs, again, how many times you read the book cover to cover, and a batch is how many chapters are in the book. That's it.
Great. Okay. Cool. Yeah. I think TensorFlow program. So I wrote. Are you doing this part?
I mean, I don't know if we have time because it's 3:30. I mean, it's not 3:30. What's the US time right now? It's 6:01 p.m.
Yeah.
Okay, we're just gonna encourage you to go ahead and check it out yourselves. But yeah,
it's fun.
Go ahead, Samrat.
Yeah, I was just saying it's fun. You might as well do it. So again, we're putting all the resources to practice all this stuff in your free time. So yeah, just some additional readings. I highly recommend looking at 3 Blue 1 Brown. Oh, my bad. 3 Blue 1 Brown if you're really interested in like the more detailed side of things. So like how neural network works, like more mathematically. He makes it really interesting. It's like he's listening to a story or something. But Google Colab, of course, because we're going to be doing a project this semester in that, so you might as well learn a bit more. And the last thing before y'all go is we have to announce the project. And I don't think we have a slide for that, do we?
No, we just say it.
Oh, okay. So a drum roll, please.
Do you want to do it or should I, Sammy?
I think you should do it.
Okay. All right. So the lovely project team here at BigTh have put together a project for all you wonderful human beings. And we are going to begin that project 2 weeks from now. So next week, we're going to be talking about we're going to be showing you and walking you through an example of an AI using a convolutional neural network to solve a problem. If anyone can guess the first problem that we're going to solve, okay, we'll figure something out for them. But yeah, we're going to show you like a solved example. And then 2 weeks from now, you guys are going to be making an AI. Dang it, Luke got it. Yeah, we're classifying numbers in the MNIST data set. Okay, but your project is going to be identifying whether a cell has malaria or not. We have pictures of cells. We're going to feed it into your AI that you're going to build, and you're going to tell us with a certain accuracy whether the cell has malaria or not. It sounds simple. It is sort of simple, but and that's because we're doing a lot of the data pre-processing stuff, but you need to know what we talked about today in order to do that project. It'll be fun. We're here to help. We're going to help you through the project as well. It's going to be fun. So that is the project announcement.
To reiterate, the MNIST data set, it's really just like a practice round, if you will, for what we're going to be doing in a bigger malaria machine learning problem. So yeah, be there for those 2 meetings. That'll be really fun. And we'll be putting you guys in groups. I'm not sure about the exact details about that. Depends on I don't know what just happened there. You didn't hear that, right?
No, that's fine.
Okay, good. We don't know the exact details about putting you guys in groups, but we will let you know as soon as we get like a more stable number of people and stuff like that. We'll probably send a form or something so we can put you guys in groups. But yeah, that's it for now. Don't want to keep you all for too long. So if you have any questions, concerns, comments, just let me know. Otherwise, we'll see you next week.
Yes, stick around or hit us up on Discord for questions or just talking and stuff. Thank you guys for coming. Thank you.
Oh, and don't forget to fill out the feedback form. That
Yes, there's a feedback form in the chat.